Welcome back, everybody, to, as Professor Ashcraft says, the happiest place on earth. I can't think of a place I'd rather be than right here with you guys. Unfortunately, I'm not right here with you guys. I am here with Professor Ashcraft, which is pretty darn great, but I'd rather be here with you. Sorry, Professor Ashcraft, it's true.
Yeah, that's fine.
That being said, we make the most of the situation we've got, and let's do some physics. So, last time we were meeting, we were talking about capacitors, and we put capacitors into combinations. So we had a single capacitor, like this, and we would attach it to a battery. Battery looks like this. Sometimes you'll see batteries drawn with two sets of these. I'm kind of lazy though. The big long line is the positive terminal. The little short line is the negative terminal.
So why are there two sets of them sometimes?
Sometimes you have multiple batteries in a pack.
Oh, okay. So if you have three of them, that means you have three batteries.
Yeah.
Okay.
But I'm kind of lazy. I made
Cool. You have one battery. Yeah.
with some voltage. In
Yeah.
this case, it would be somewhere in the vicinity of a 3 volt, because that's what it says.
Cool.
All right, so that's if we have a single capacitor attached to a single battery. Very simple circuit, but we have slightly more complicated circuits we can make. We could add our battery here, and we could have a capacitor, C1, and we could have a capacitor, C2, attached back down to the battery. Slightly more complicated circuit, right? We have double the number of capacitors. When they're in a row like this, when there's only one path that you can go through in this circuit, remember what that's called? Professor Ashcraft, do you remember what that's called?
That was a series, wasn't it?
It is. It is a series, and I knew you knew that answer, but I don't know if you guys on the camera did. You should. If you're in my lecture, you should pay attention. So there's only one path to go through. That's a series. 1, 2, boom. There's another opportunity there, another option here. We can, instead of making one path, we can have a junction where it splits and have two paths. Oh, I'm going to draw that a little lower. Have our battery down here. We can have one path here with a capacitor C1, and one path here in the middle with our capacitor C2. Oh, I have a quick question for you, Professor Ashcraft. What would happen if I moved this C2? What if I put it over here? That's not drawn the same, but it is the same. I just took C2, I moved it to here.
Well, it looks like it's still in series. I mean, because the wire is yeah, it's still in series.
As far as electricity is concerned, that wire is all the same place. It makes no difference how long it is. It's a conductor, it makes no difference. It's got zero resistance in theory. In reality, there's some. And if I have a really, really long wire, it's going to affect the circuit. But over short distances, it doesn't. We consider the resistance of the conductor zero, and therefore it has no drop in the voltage, which means that it doesn't matter if they're right next to each other or if they're spread out, as long as it goes in this order through the circuit, where the current would have to go. If I trace a line through the circuit, it has to go through C1, then it has to go through C2. Now, I misspoke. Professor Ashcraft always holds me to this stuff. In reality, there is no current going through C1, and there's no current going through C2, because there's a break, right? There's a gap. So there's no current that goes through them. They get charged up, and there are charges moving, but nothing is going from here over to them. So that's an important theoretical mindset you have to keep in mind. But if I'm drawing my finger through the circuit, there's only one path for it to go through. In this one, my finger has options. There's a junction, an intersection. I could go this way, I can go that way. It doesn't matter where on here that is located. It doesn't matter if C1 is over on this part or on that part. As long as it's in between these two junctions on that branch, it's always going to be the same. It's always in parallel.
Yeah, lots of times we talk about electrons having a choice of where to go. Electrons don't have a mind, don't have a choice.
No, but they do have possibilities.
Yes.
Right?
It's a nice way of thinking of it.
Okay, so my point there is, sometimes when I'm building my circuit up here, it will look slightly different than maybe the drawing or what you would have done yourself. But as long as they're theoretically the same, then it doesn't make any difference. Okay, cool. Now, lately we've been talking about, we've shifted gears. We were talking about capacitors, but lately we've been talking about, I think, resistors. Now resistors, they do allow current to go through, but they do resist that current. That's their job. Resistors resist current. Instead of drawing capacitors on here, I could do the same thing, but with resistors. A very simple circuit might have a battery. And then this little sawtooth thing, which you know is a resistor. It has some resistance. And this has some voltage. Very simple circuit. One resistor, one battery. And we'll have some current. In this case, now we actually do have some current going through. All right, awesome. But just like capacitors, we can put these in combinations. And just like capacitors, we have two options. Where before we had series of capacitors and parallel capacitors, we can have series of resistors and parallel resistors. So I can do the same drawings. We'll have R1, R2.
Hey, when you drew that, your pen never left the board.
Yeah, because it's a series, one path. As opposed to parallel, where there are multiple paths. I had to pick my marker up.
Mm-hmm.
Now remember last time when we were doing the capacitors and we said that there is a theoretical equivalent capacitor that I could replace these two with that would do the same exact job? Because putting them in series changes the capacitance of the overall set, and putting them in parallel changes the capacitance of the overall parallel set. Same thing is true with resistors. When I put a resistor in series, it changes the resistance of the overall. When I put a resistor in parallel, it changes the resistance overall. So, just like before, we had parallel capacitors, series capacitors. We have parallel resistors, series resistors. And we have a change in the overall capacitance. We're going to have a change in the overall resistance. You're going to learn very soon how to calculate those changes and those equivalent resistances. But today we're just going to toy around with the qualitative aspect. We're not going to get into too much math today, which is kind of nice. Today we're just going to be exploring the effects of this, not really the numerical aspect, the calculations. We're just going to look at things and see how they're affected by adding resistors. The resistors we're going to add are, I guess, nice ones that glow. Check this out. If I connect this to a battery, it's just a light bulb, but I mean still it's kind of nice. A light bulb is a resistor, and it's going to have a small amount of resistance, but it does act like a resistor would when I put it in the circuit, and we'll be able to see the effects in how bright the light bulb is going to glow. Okay, so the first thing we're supposed to do is hook up a circuit with a battery and one light bulb. So I'm going to hook up my battery here. I'm going to hook up my light bulb right there. I'm going to get a couple of these threes. I don't know why I picked the threes, I just like the threes. And you can see how bright that is. What do you want to call that? Fairly bright?
I was going to call it bright.
Okay, that's all good. You guys
Bright.
can call it what you want it. Just call it bright. All right, on to the next page. 2 bulbs in series. Now, how do I want to wire this? I think this is fun. It's like grown-up Legos. I guess Legos are grown-up Legos too if you really want to play with them. I'm going to connect these two right in series. The key, remember, is one single path. So if I go from the positive, I need to connect to here, and then it's got one way to get there.
So if they don't do exactly like you do, they're still right.
They might still be right. It can be different than this and still be right.
Okay.
Yeah. There are ways that are different that are wrong, but as long as it's in series, as long as there's one path, then it's correct. Now that does look different than it did before.
Yeah, that's not as bright.
Definitely less bright. These are equally bright. The 2 bulbs are the same brightness,
Okay.
but they are less bright than the one before. And I can show you that just by moving this over here.
Ooh, yeah.
Now, this is kind of cool. I don't know if this is in the lab or not, but why isn't this one glowing? It only glows when current goes through it. And current only goes through it when we have a closed circuit. This branch of the circuit, it doesn't go anywhere. It's not connected. There's no voltage difference across it. We get a current flowing when we have a voltage difference. There's no voltage difference from here to here. definitely less bright.
Mm-hmm, mm-hmm.
All right, so it asks a series of questions about that. You can answer those on your own. I don't think I need to show anything else. So these are the same brightness as each other, but less bright than it was before. Wow, we're already on part 3. Oh, this one goes fast.
It does.
Now I need to figure out a way to make these 2 bulbs in parallel with each other. Now, I see a lot of different ways to do this wrong. The key here, this is really, I think, the most important part. Maybe I'm wrong, but Professor Ashcraft will correct me if I am.
Oh, yes.
The key here is that 2 sides of the 2 bulbs need to be connected to one terminal, and the other 2 sides of the 2 bulbs need to be connected to the other terminal.
Mm-hmm.
They're connected to each other, so the 2 sides, in my left here, my left hand is touching the 2 terminals or 2 sides of this bulb.
Mm-hmm.
And those 2 sides are connected to each other and connected to the negative terminal of the battery. There's lots of different ways to do this right, but there's also lots of ways to do it wrong. So these 2 are connected to that terminal.
Yes.
They can be connected like that, you're right.
Right.
But they're still connected to each other by conducting wires
Yes.
with a battery in the middle.
Yeah.
Or I can connect this one here, and then this one to that. So they're all connected. Terminal, side 1 of bulb 1, side 1 of bulb 2.
Mhm.
And then on the other side, we have terminal, side 1 of bulb 1, or side 2 of bulb 1, and side 2 of bulb 2.
That works.
That was a lot of talking to get us to this point. But I want you to see how bright those bulbs are.
Those are bright.
They're pretty bright. Are they brighter than they were before? Well, that's what it was before. That's when there's just one hooked up. And that's what it is now when there's 2. I don't see any difference. Do you see any difference?
No, the first one's not affected.
So they're in parallel now. Notice that there's a junction right here, so it comes from the battery terminal out, and electrons can go this way, or they can go that way.
Uh-huh.
So there's a junction, which means we're in parallel. And the brightness hasn't changed from a single bulb. So if it was bright with a single bulb, it is now bright with 2 bulbs in parallel.
Uh-huh.
It's brighter than it was in series, but it's equivalently bright to what it was in parallel, and they're equivalently bright to each other.
You know what this reminds me of?
No.
Food.
Tell me.
Okay, imagine you have a pizza. Imagine I have a pizza, okay? I got this, like this little pizza. And then all of a sudden you show up at my house.
All right.
Well, what do? I cut the pizza in half. I give you half, I keep half.
You're kind of generous.
Yeah, and then all of a sudden Joey comes up like with his bike. Well, what do I do now? Well, we cut the pizza in thirds, right?
Sure.
So with each person, we get less pizza.
Yeah.
That reminded me of the series. Because when I had one bulb, I had all of myself. And when I had a second bulb, it got dimmer.
Yep.
Kind of like I had less food.
That's right.
This reminds me when I make a crock pot full of chili.
All right.
I have a bowl of chili and you drop by, I don't care, because you get your own bowl of chili.
I get my own.
Your bowl of chili does not affect my bowl of chili. If Joey came by, he could have chili too, I don't care.
And by chili, of course, we mean voltage.
Yes.
Love it. That's awesome. And now I'm hungry.
Well, yeah, because I always think about food.
Okay. So if putting things in series is fun and putting things in parallel is fun, putting them in series and parallel at the same time is going to be twice as much fun. It's like fun squared.
Is that like pizza and chili?
That's like having pizza chili.
Whoa!
Chili pizza.
Okay.
I don't even know what that would be. All right. So now we're going to make some combination. We're going to make a combination of series and parallel. And there's a bunch of different combinations that you can make. I'm going to make a combination where it's going to go set one resistor in parallel, or oh my gosh, I'm going to edit this. Okay, I am going to make mine such that there's a bulb in series with a parallel set of bulbs. So we'll have 2 bulbs that are in parallel with each other, and that parallel set is going to be in series with a 3rd bulb.
I got you.
I could put 2 in series and have that series in parallel with a single.
Mm-hmm.
There's lots of different ways that I can make this.
Mm-hmm.
This is just the way that I'm going to make it.
All right.
And I'm doing it because it's drawn in my notebook. That's the way I have it drawn over here. I'm gonna put the battery over here. Yeah, I'm gonna put the battery over here. I'm gonna move it over just a little bit more. I'm minimizing the amount of stuff that I need to make it. Move it down here so it's separate. All right, so not done yet, but I'm showing you what I've done so far. I've got the positive terminal right here. Current will come out, go through bulb 1. It's going to leave bulb 1, come around. I haven't built this part yet, but it's in the construction. It's going to come in. Now there's a junction. It's going to split off, and I have these two in parallel with each other. Professor Ashcraft, do you have any guesses as to what this is going to look like?
I'm hoping all 3 bulbs are going to be lit.
I'm hoping so too. We know when putting things in series, it seems like they get dimmer.
Yeah.
In parallel, they don't really get dimmer.
Right.
But when they're in series, they do. So.
Yeah, so your one should be bright, and your ones in series should be dim. I hope.
Let's find out. I'm going to turn the lights up because I can see them. These are lit, but very, very low amount of light. And this one is bright. It's not as bright as it would be, I think, as if it was the only one.
Well, if those two weren't lit, if no current was going through, then the other one wouldn't have any current in it.
So, I don't know if you can see it. I hope you can. There's a little tiny glowing spot in bulb A and a little tiny glowing spot in bulb B in the parallel set. What's wrong? So, you're going to need to make some observations.
You said in the parallel set.
Here's the parallel set.
Okay.
They're very dim.
Okay, the 2 that are parallel.
They are lit,
Right.
but just barely.
Okay. And then the single one is in series
It is.
with the 2 in parallel.
Correct.
Okay.
So positive terminal,
Right?
bulb.
So all the current goes through that one single guy.
Yep. We
Okay.
get up here, it splits.
Okay.
Some of the current's going to go this way, some of the current's going to go that way.
So-
Going through here, and then coming back together and getting to the negative terminal.
So then the current is shared between those 2 really dim guys.
Yep.
They're really dim.
Yep.
Okay.
All right, so based on those observations, there's a table you're going to fill out in part 4, and then some questions you're going to answer. There is a mathematical formula here that says power equals current times the voltage, and you're going to do a couple calculations, not really calculations, you're not putting numbers in, you're just moving things around to answer the questions. And actually, I think that's it.
A lot of my students like to do this for their extended lab report because they think it's nice and easy and short and things like that. But they don't do a good job on it. They don't give the theory and they end up with a low mark.
It's all theory. And if you don't do a sufficient job explaining the theory in this, since there aren't any mathematical components to buffet that, or to buffer that, then yeah, you're going to be in trouble.
Yeah.
All right, folks, that was a short, quick lab for you guys to get a basic idea of a qualitative understanding, to internalize some of these things that are happening. It's hard to see because you don't see electrons moving, right? But we get to see here the effects of it. And I hope that helps you understand some of the stuff we're talking about in the lecture down the hall. Thanks, everybody. Have a great day.